going to continue talking about similar triangles, and this time we're going to talk about, well, there's actually more than one way to use similar triangles and how to prove them. We also have a side-side-side and a side-angle-side similarity to discuss. So in number 5, we have a proportion. So we're saying that A, well, there's going to be there. So AB over DE, so we have the bottoms of those triangles, is the same as BC over EF, so another set of corresponding sides, which is the same as AC over DF. Now my dots here, they're just showing that what's corresponding, because we don't necessarily know that they are congruent, we know that they're in proportion. Now, since all 3 sides are in proportion, that's the other half of my similarity theorem. I now know that triangle ABC is similar to triangle DEF. And so what I'm going to say is that if 3 sets of corresponding sides of 2 triangles are in proportion, then the triangles are similar. So now I'm trying to prove that angle B is congruent to angle E. So absolutely. Now angle B congruent to angle E, because now I have corresponding angles. So my corresponding angles in similar triangles are congruent. Now it says to describe a series of similarity transformations that will map ABC onto DEF. So the very first thing I want to do is I want to get these triangles on top of each other. So I'm first going to move and get my one triangle onto the other triangle. So we are going to translate triangle ABC along vector AD. We're just trying to get A to map onto D. So point A, whoop, not just point A maps onto point D. Okay? Now, once I translate that, now I need to use some sort of dilation. So we are going to dilate triangle ABC using a scale factor, and I'm going to say DE over AB, and again, I can pick any corresponding sides that I want there, so that if I multiply my scale factor times my small side, I get my large side, and we're dilating this from point A or D, such that point B maps onto point E, and point C maps onto point F. So we know that translations preserve angle measures. And congruence. We know that dilations also preserve angle measures. my conclusion then, therefore, triangle ABC maps directly onto triangle DEF. All right, and moving on to our next one. We have a proportion where we have VZ over XZ equals WZ over YZ. So we know that we already have a proportion. So now we have two sides that are in proportion. But remember, if I want to use side, 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 I need three sets of sides. So what I'm going to do next is I'm going to use a combination of my sides and an angle. So I'm going to say in step 2 that angle Z is congruent to itself. So number 2 is our reflexive property. Now that I know that that's reflexive, I know that my two triangles are similar to each other. So triangle ZVW, similar to triangle CXY. And my reason is, if an angle of a triangle is congruent to the corresponding angle of another triangle, and the lengths of the sides including these angles are in proportion, the triangles are similar to each other. So now that I know that those triangles are similar to each other, I can finish this up. I'll know step 4, I'll know that angle 1 is congruent to angle 2 because we have the corresponding angles in similar triangles are congruent. Now, if I want to prove that this is similar by using transformations, so what I want to do is I want to use another dilation. Right? So I'm going to dilate triangle CVW, whoopsies, through Z, using my scale factor, something like XY over VW. The way that I want to double check that is that my K times my VW equals my XY, whatever my scale factor is. So we have V is going to map to X, W is going to map to Y, and Z is going to map to itself. We know that dilations preserve our angle measures. So now I know that my triangle CVW similar to triangle CXY.